Okay, so our next speaker is Professor Jorge Diaz. He's an assistant professor. He's a professor at the Center of Autonomous Robotic Systems in Khalifa University. And his talk will be about neuromorphic computing architectures for robot vision and marine harsh environment. Okay, Professor Jorge, the floors are yours.
Hello, good afternoon. So the title of my talk is a little strange, right? But actually, I intend to be a little provocative today because I think many people is using a lot of data nowadays. Many people using numbers that they put in the computer, but in fact, we still have a need to looking for the computing aspect that put the machines working properly in the robotic side. Actually, if you like to see how robots work, basically they are a little different than just a computer. Why? Because they have the property of motion and they need to move, and they need to move with a purpose. Okay, so basically, if you have some machine that can do that, if you have a machine that can do what we like many of biologists here trying to do, pick up the opportunity of surveying is very good. So nowadays, we have very well-defined areas that are in the robotic side. I put here these 3 circles. Some of them are related with the mobility and control. This is the classical way of seeing the robots. Then we have another community looking for the data that this robot can acquire around. And then is reasoning. The reasoning is looking for what we see and make a decision. And this is when comes the problematic part of robotics. And nowadays, when we talk about autonomy, we talk about better decisions with better knowledge, what we see, better understanding what is around us, and really decide the correct purpose of the robot, including, for example, interventions. So the area is quite large, and this is just one pie where you can see how much the things are. You know, we have lots of different areas here. And many people that work in robotics nowadays, they feel a big dilemma. They don't know if they are computer scientists, if they are mechanical scientists, they are from aeronautics, if they are, so it's a big dilemma. But in fact, what happened is that we are in the front of a new discipline. Is a discipline of robotics, and in fact, this is some kind of understanding by the people nowadays that is really an area that converges many things. Converge for machines that are intelligent, machines that put us dreaming on things like going very deep on the water, looking for things that are impossible the human being doing, and maybe just doing what we like to do in the place, but it cannot be there, okay? So basically, along years, we see happening developments that is just one line of time showing different dreams appearing along the time. And in fact, what we can see along this line is that more and more the intelligent part appears. The intelligent part nowadays came more by the way you run algorithms. These algorithms is very interesting that are normally associated programs, but maybe it's not just programs. Maybe it's just the way we also put intelligence on the materials, also in the electronics. And this is very important because the dilemma that we have nowadays in the robotics fields is trying to do robots that are different from what we have now. Different because they don't just use electronics. Maybe they use intelligence embedded on the material itself. And we have nowadays areas in robotics like soft robots that can do manipulation very soft way, and it can be very effective. But in fact, all them trying to make it probably very simple autonomous systems. Some of them probably simple enough, just observe what you see around you, okay? One fact, and now coming from this dream of robots that are intelligent in the total, nowadays what we see in our area and technology domain, and I'm talking as an engineer now, we see that we have a lot of data. You know, sensors are available. We have a lot of sensors of different kinds, and we accumulate this data. You put everything in the memory. You also correlate this with time, and you can start looking for these things like, okay, why this happened and this also happened? Maybe they have some correlation. Maybe you can have some mechanism of, if this happen again, maybe I have a prediction about these things. And in fact, is what is happening now. What is happening now is that some tools that come from another domain is not new tools actually. These tools coming from the machine learning that looking for the numbers in different way. And that the people call it machine learning. And in fact, there are the extension of statistics and somehow mix it with some computer science. And we start to have mechanisms to pruning and let's say aggregate information that are important for us on the data. And what happens nowadays, we that acquire all these things, maybe in the machines that you put in the water, and then you don't have memory to put all these things. And it's very funny. We have a huge problem. We have a lot of data. We don't have mechanism to accumulate it. So how we should solve this problem? And if you see what is happening, in fact, these techniques of machine learning, more than just a new trend, is also a good way to compress the information. In fact, they are aggregating, they are making just another level of representation of the knowledge that we have. So it's just not just raw sensors, it's a little more than raw sensors. And we have continuous mechanism of publishing people using these tools all over and found very interesting things. This is just one accumulation of data that we see, articles along the years when we see an explosion of these new articles on the area. And is actually, I'm coming from robotics. I remember 2 years ago or 3 years ago, I'm fed up, and me and another people are so much articles on deep learning, nothing more in robotics. In robotics conference, more than 75% of the articles are just machine learning and deep learning. It's too much, actually. They are not solving nothing because they don't really explain physically nothing. It just explain relation between numbers, and they are not used properly. And in fact, the engineering that we have nowadays is not helping too much how we use these tools. In fact, we have this kind of paradigm of data science, and the data science have two parts: data engineering and then application of the tools. This is the oracle nowadays. But in fact, probably need to involve a little more about this. And it's interesting to see this pipeline that we have, data science, and then data collection, and a part that is applying this machine learning tools. We probably need to see it a little more closest. One part we know, the people that work in the area know, that how hard it is to apply these data schemes that we have nowadays, where you need to annotate data, spend hours and hours annotate the data and fine-tuning parameters to put the algorithm running very well. And also we have another, this is one effect that we have. Another effect is that somehow the people that develop electronics somehow push us much more and more to use clouds, put the things in the cloud, put things in the use servers, and then they also open services that we can use it and use this data. And in fact, we have one industry that is looking for this high performance computing nowadays. But however, this kind of thing maybe needs to be changed, because in fact, probably what happened is that this kind of machines that we have nowadays to compute and manipulate the data using the algorithms that we have, using the Von-Neumann architecture that some of you maybe know, needs to be reiterated and be rethinking, okay? In fact, the first interesting thing is that when you see the things from the perspective of computing, and in one important aspect, the evolution that you have nowadays in robots is funny, is coming by the computing part, is by the algorithms part, is by the way you make the operations, you know, multiplications and sums and so on. In fact, is the computing is embedded on these algorithms. And when you see this and you try to see the workload when you do the computation, you see the training is very, very expensive and iterative. You know, this is one aspect. And then when you have all the data available and all the numbers are okay, and then you just put in the machine and then you make the inference very fast. So the problem is always this training mechanism, you know, this training mechanism that we do the exercise nowadays like this, you know, you put this thing here, that is our cycle that you have in robot side. You have, you know, algorithms running here, here, and here, and then you do it on stacks that are, you know, softwares that you make aggregated on libraries, and then you run it this in very interesting things. You will use your C++ machine, you put in the desktop. Sometimes you have these GPU accelerators that you love so much. And GPUs, actually, just a reminder, GPU was invented to do this graphics on games. You know, it was fitted to the games, you know, more than just manipulation for numbers, you know. So these GPUs are used to speed up. But in fact, probably you need to look at this thing in a different way. And this is what we'll talk today. In fact, when you do these machine learning aspects, in fact, if you look for the background of machine learning, is coming from the area that we call it artificial intelligence. And artificial intelligence should look for the intelligence itself. And there are, in fact, paradigms or principles that are coming so long time ago that are somehow related with what we call it brain-inspired paradigms of computing. And the funny thing is that many people start thinking, oh, we have this idea of perceptron, or this idea of neuromorphic approach. And I discovered recently this kind of thing is coming 1990. You know, in 1919, this gentleman, Carver Mead, it was a fellow from IEEE, just invented this perceptron, and in fact was telling that in fact you can have very interesting computing based in very simple mechanisms. What is the simple mechanism? You have a model, you make a prediction with this model, you compare this with your desire, like the input, and then you just make a correction and adjust the model again. It's more or less the principle of feedback, that you adjust some kind of model here that in fact can be just a weight or something like that. And in fact, this kind of principle that was very old, it was nowadays and after some time appear as artificial neural networks. And if you look for this principle, artificial neural networks, what is this? In fact, from computing side, is just a weighted sum, okay? And let's tell this, okay? And the weighted sum, that you need to do it in a computer. Why this is interesting to say this way? Because probably the machines that do this weighting sum are not doing well. In fact, the way we do it nowadays is organized with some mechanism. We have a CPU memory in one side, you know, where you just allocate some part of the memory, just passing the information from the CPU to the machine, to the operator itself, and then you process input to output by using the memory all the time. So if you see this paradigm is the von Neumann paradigm that is very well known, is used in these computers nowadays. We use it for very high specialized, but all the time. And we extended this to GPUs, you know, and this is in fact something that we need to think about is remove this principle and put another principle, maybe just oriented more to some kind of special way of doing this neural networks weighted sum that imitates really the brain itself. And you have, in fact, if you do that, you do it in such a way that also make a more efficient computing. Why? Because what happens nowadays with these CPUs and GPUs that you have, we extended the maximum we can, the physical support to make all these bits and bytes and memory that you have, and all these instructions that you have inside of CPUs, maybe optimizing some architectures, but some barriers are appearing now. We have a barrier of dimension, heat, all that kind of things. And you need to start thinking in different paradigms. And one of the paradigms probably is like, you know, looking for this neuromorphic mechanism, like the previous one that I mentioned. And when you do that, we starting to see that some people have good ways of doing this neuromorphic in different ways. The first one is one that I'm promoting here. Maybe some of you already know about it, is neuromorphic sensing. That is no more than just some kind of camera that what we do, you acquire images, but what you just grab is impulse for things that change on the image. You see the dynamics, you see the derivative, you see something that change. And when you do this, and this is possible to have nowadays with cameras like this one, you know, you have some people doing it. It's interesting that you can compress a lot your data. And in fact, more than just compressing the data, that is much more less, is it's not all this volume of numbers that you have. Maybe you find interesting things. I have just one example here. I'm trying just to put it here. And this is a common situation where we have one camera looking for around, and you see black things here. This camera now is the same thing, but after superimpose the event camera, and you start seeing that this is dark, but here is not dark. You see things happening here. So what happens between this left side and the right side is superimposing in the image that we normally see it very well. We superimpose the event of change, okay? So what happened is that this event will be just an interesting aspect that you don't see just by the one image. And with the fact is that you also compress the image. So you have two effects here. One effect that you compress, another effect that you see things that normally you don't see it before. How this can be useful? It can be useful in different ways. If you try to interpret, for example, data that you have here in this card, different illuminations, you start seeing things like this. But in fact, these kind of things can be filtered by image processing very, very easily to you understand where you are crossing. For example, I give in one example here that we did some tests during the night with the similar situation as before. We have in the left side, you know, someone moving a car during the night, and then the same person with the same camera, but now superimposing the data coming from the event cameras, and you can start seeing that here you don't see nothing basically, and here you start seeing some kind of contours that you can use it for your navigation. So this kind of thing that looks so simple, like just pick up the derivative, nowadays is explored by the community very, very much. And I must tell you that you can nowadays, using this kind of technology that is sensor-based, it's just a neuromorphic principle. You're just looking for the difference. And this is actually this very well-known neuromorphic sensing mechanism that is used by some of my colleagues. And we can do it nowadays with different aspects. You can make object detection in a different way. You can have tracking that is much faster. You can localize and mapping. You can do your SLAM more faster, okay? So this is just one approach for neuromorphic sensors itself. But if you look now for the other part, that is really the computing part, that is really the architecture that we have nowadays for the computing part, we have two big trends. The trend that they call is trends based on the neural networks itself, that is what the people normally use it, or the spiking mechanism that you use you convert numbers as spikes, okay? Spikes, and I will elaborate a little bit more about that. So coming back to the deep neural networks, that is the technology that we have nowadays, and many people is using. Basically, thing that we have is that we have aggregations like these ones. We have some weights here. They have a hidden layer that is something that converts the inputs that you receive from other nodes here. This is the input layer, this output layer that you can elaborate a little more with more deep, let's say, mechanism. Some of the interesting things that we have is that some of these weights that you use is funny. They can be really optimized. That some of these weights that you use with different inputs and you make the sum, there are repetitions of this small multiplication here. And we don't care nowadays. But in fact, this repetition is there. You make a multiplication, and this multiplication appears several times in the data, and we are not using this. And we should start looking for these kind of things. And in fact, when we come for the deep learning mechanism where this multiplication becomes exhaustively and heavy, where we have different layers of this kind of, multiplications and sums and so on, we need really to have optimizations on the mechanisms that you do it. Now, people working in this area, fortunately, we have some CPUs targeting this kind of multiplications. We have some vendors trying to do it better than before. We see it in different kind of vendors. NVIDIA is well known by that, and we have all the time trying to sell it as a mechanism to do this computing more faster. But the interesting thing is that becomes another players. We have a new players that come in, like Samsung, that are trying to explore this idea of a CPU that is looking for this deep learning mechanism. However, when we trying to do one movement to try to go from the GPUs to this new kind of trend, you need to pay attention. One part is that you need to pay this bill of new kind of engineering. You don't know the programming as before. You need to be careful with that, and you need to have some kind of mechanism to evaluate the things properly. Actually becomes like also a correct way of using the architectures of computing, depending of the way you use the neural networks. So there are several types of networks. Nowadays, many people use these ones and transformers and other ones. And all these ones, you apply it differently, and you need to be careful the way you use it. But in fact, the things that you need to think about is mainly the big problem is you should avoid architectures that make the transfer of data. In fact, if you looking for the energy side, or also by the time that you need to transfer data between the memory and the computer, if you make some studies, for example, with situations we have just a dynamic RAM and a processor, if you use this kind of architecture without using a buffer or using a special kind of architecture, you can pay the bill of 200 more energy than usual. So we need to pay attention when you put something inside of underwater device. If you want to be fast, you need to look for these specific things. It's not just buying something and use it, you know. So it's very important. And also sometimes you need to think about the way you do this kind of use of the weighting and so on. So basically, there are interesting aspects that I never thought. There are transformations that you need to think about that can be useful sometimes to simplify our programming, using also this kind of machines for doing computing. And this is areas that we have that are interesting for some of you. Maybe you if you're looking for the way you allocate the weights on the neural network, sometimes the weights are so sparse that are not neither important, so you can discard partially the things that you have. Just part of the network is important for the optimization of the process, and all this kind of attitude and engineering about this data becomes a very different. Okay, one aspect that you like to talk with you is that sometimes the algorithms are different also by the way you implement them. And one important technology that we have nowadays is what we call this FPGAs that are optimal in the sense they are using just the correct resources for the correct computing. And this is, you need to pay attention on this. Probably is, if you are interested on making this faster, on the less energy, and you have some kind of technologies that helps to do this. And this is one of the cases. We just do the same kind of things like using PyTorch. You can use also with the FPGAs. Some vendors already trying to do this very fast. I just give an example that I like it very much. Our colleagues from MIT some years ago, they developed something that are very simple. You see here a very complex, you know, system around a small quadrotor that is this one here. And this very complex system that includes RunSack, includes stereo, and uses this RunSack for this mapping part. You can have also part that you have a tracking part that you use different kind of sensing part. So they use it, interesting thing in real time. And this is just one example that you can see work in real time like here. And funny, when you see this, oh, this is probably very complex, you know? So you see points coming and you'll see again moving and very fast. And the camera is moving here. And if you see this thing, oh, this should be a big machine in the back. In fact, it's not true. The machine, you'll see in the right side, it will appear here. Is this machine here? Actually, is this thing here? Okay? So you can put all this artery of algorithms inside of small thing. And this is really important to start thinking that we need to looking for the computing the different way. This is my contribution as engineer for the area of robotics and people that need to do with robots that are more, let's say, associated with fast. And one important aspect, maybe you are interested to look at this in the future. We actually, in Khalifa University, we are doing this now. We're looking for the spiking mechanism. That is another way of looking for this weighting mechanism. What happens is that you convert numbers not as numbers with lots of bits. We have just impulse, and this is the impulse. You reduce a lot things. You reduce IRs. You don't have 16 bits, you have just one and impulses there. So, and you have this spike in neural networks nowadays that works quite well, and you can convert it using this low heat system that you have, and we are exploring now with the Intel. In fact, we have, for sake of people that are interested in the area, we have already some kind of mechanisms to support this programming. So you have the application and interface use LOI, and you can develop everything you know, on the software side with this tool here. So we have tools nowadays to do this, and Intel is promoting this nowadays. We have also another ones for IBM, but let's say I myself looking for more the Intel side. What is interesting to tell about is era of metrics that we have nowadays when you compare computing. Normally, we're looking for the metrics by this way, you know, signal noise ratio, you know, the errors that we have in numbers, and accuracy, runtime. When you're looking for the hardware side, we start extending this, and we have another names that you need to take in consideration, and very important for the engineering aspect of the robots, you know, the latency, the energy and power, the hardware cost. All these kind of things now maybe is a little more expensive, but in fact, they will be less expensive with time because it's using less energy by the way you do this computation. And I'm like just to showing to you what are our latest results we have on the image de-hazing. We applying this on the underwater images to achieve images like these ones. It's quite interesting. We compare these techniques with the techniques where we have classical models. In fact, the idea is to improve the images itself, like some of the images that you have here that are blurry and you cannot see it very well. And you can do it in a very fast way with things that you can recover in this form. So nowadays, we can do it very fast, this recovering, and you can put inside of a computer, do it immediately, okay? So there are several techniques that we use nowadays. Mainly, we are applying deep learning techniques. We have some, we can have some discussion about this. We have some kind of neural networks. So we are exploring now more these vision transformers that improves the images like these ones. And yes, this is more or less what we are doing nowadays, using this spiking mechanism and also applying with reconfigurable techniques. This work right now is using not the GPU like you see it, but what we call it OpenCL kernel that we just compile immediately the modules that you need for the computer and you put in inside of a board. So nowadays you just have the hardware that you need to do the computing. You don't put more. You don't put memory that you use once and never use it again, okay, and spending time. So spiking neural networks is also another thing that we are doing now. And right now we see something that is done for the training set we have. So we have basically two areas that we are working: neural networks and speeding the computing in the neural networks. Another one using events, and the other one is spiking part that we intend to do. And our first results are quite okay. We are adjusting the time that we generate spikes and make the reconstruction now. And we have some work that we are doing now. So we apply this for different things. We are just doing a very crazy thing like multimodal pose estimation using the composition of inertial sensing with images at the same time using spike. And that is quite promising. And we just have a combination of formal modules with the other ones. And this is an area that I'd like to say. Yes, and one of my master students just starts trying to sell himself and said, oh, I can also try to do detection of cracks under the water. Let's try to do it. So he did some work on this crack detection, in fact. He makes some initial tests in the pool, and this is the kind of makes some emulation of cracks on the tube, and he have some results using this spiking mechanism, using you know, like a spike SSN, and then generate the reconstruction the other side. So how we do it? the world. The together. And yes, this is the contribution for the area that I give it to you. So my sharing with you that are end users and also some technicians. I didn't know what kind of public is here, but if I talk as engineers, you need to start thinking in another paradigms of using computing, not these ones. You stop someday, okay? So you need to start looking for another ones, okay? The word neuromorphic appears, but it's not more than just an idea of inspired by the brain aspects and this weighted sum. And nowadays it's not difficult to do that. In fact, you can do it in real time using, FPGAs. That is, it can make it, very compact, or using this hardware from Intel. If you feel that are ignorant in the area, you don't have any problem. You are not alone, because many people is learning. We have some people that are pushing for these kind of things. We have hardware design people that are, doing important textbooks and so on. And we are growing a community on this. And in fact, one important aspect, if you trend to use the GPU trend that is nowadays high performance computing, like this, use it in this car, probably you don't have space for the computer to make this car intelligent enough. If you want to make this car very intelligent, you don't have space inside of the car. So it needs to rely on the cloud. It needs to rely on the computing outside. And one day we stop consuming petrol and you start consuming another thing. Okay, so you have cars, all them consuming computing far away. So you need to really looking for another way of doing this computing and make it more efficient. Okay, this is my advice. So because someone asked me what I should push here for the industry, please, coming to these robot chips, things that you need to be customized properly for small and real time, okay? And if you have nice things done, I propose you to come to Abu Dhabi, to IRUS to 2024 on this time, okay? We are very welcome, and I'm running, and and Eric, you are a partner on this from now on, okay? Okay, thank you very much, and this is the team that I'm working with me. Yeah.